Have you ever just stopped and wondered what makes a block of solid ice behave so, well, entirely differently from the invisible water vapor floating in the air all around us? I mean, if you think about it, structurally and chemically, they are the exact same thing. It's just water. Yet one is this hard, rigid block you can physically hold in your hand, and the other is a completely invisible gas you walk right through every single day without even noticing. So, what is the hidden, invisible architecture that actually governs these wild transformations?
Well, welcome to this explainer. I am absolutely thrilled to be your master teacher today. We are going to take a deep dive into the fascinating world of grade 7 science, specifically following the Matatog curriculum's exploration into the states of matter. We're going to visualize exactly how this invisible microscopic world operates, and together we'll unlock some of the most fundamental secrets of chemistry. It's going to be a lot of fun. All right, here is our quick roadmap for today's journey. 1. The rulebook of matter. 2. Solids, liquids, and gases. 3. Heating up, adding energy. 4. Cooling down, removing energy. And finally, number 5, phase changes in reality.
Okay, let's jump right into section 1, the rulebook of matter.
Okay, let's dive into this, because before we can understand exactly how ice melts or water boils, we really have to establish the fundamental ground rules. The ultimate rulebook for matter is called the kinetic molecular theory, or KMT for short. This theory tells us two absolutely critical things. First, all matter, literally everything around you, including your own body, is made up of these tiny invisible building blocks called particles. Second, and this is the kicker, these particles are never perfectly still. They're constantly in motion. And the secret key to all of this? The amount of that motion depends entirely on temperature.
Moving on to section 2, solids, liquids, and gases. Let's conceptually shrink ourselves down to the atomic level for a second. Focus your attention right on that first box showing a solid. Notice how those red particles are just tightly packed together? It's a highly structured, rigid, and totally orderly arrangement. Because they're so closely bound to one another, they have very minimal movement. They literally cannot wander off. They just kind of sit there and vibrate in their fixed, locked-in positions.
To really visualize this, I want you to imagine a bunch of marbles jammed incredibly close together in a tiny box. Now, if you give that box a little shake, the marbles might vibrate and rattle against each other, right? But they don't actually change their positions or swap places. They're stuck. That rigid, locked-in structure is exactly why a solid holds its specific shape. Now, let's slide over to the middle section of our diagram here, which represents a liquid. The particles are definitely still quite close to one another, but you can immediately see a huge difference. That rigid structure, it's gone. These particles have gained just enough freedom of movement to slip and slide right past each other. And that sliding action is exactly why liquids can flow and magically take the shape of whatever container you happen to pour them into. And this brilliantly illustrates our next analogy. Think of marbles sitting in a bowl. You can run your fingers right through them, and they'll roll over one another and freely change positions. But notice that they still stay relatively grouped together right down there at the bottom of the bowl. Finally, look at the third box in our diagram. This is a gas. Notice the incredibly wide spacing between all the particles? They have broken completely free from the forces that were holding them together. In a gas, particles are moving rapidly, randomly, and totally freely in all directions, just endlessly bouncing off the walls of whatever container they're in. To complete our baseline understanding, imagine someone dumped a bucket of marbles and scattered them rapidly across a massive empty room. They'd be rolling incredibly fast, bouncing off the baseboards, entirely independent of one another. That total chaotic freedom perfectly represents the everyday behavior of gas particles. All right, section 3, heating up, adding energy. What happens when we introduce a little heat? So, we know how these particles behave in isolation. But what happens when we introduce a catalyst and crank up the temperature? We are going to conceptually map out the chronological journey of adding heat energy right now. We'll watch step by step how thermal energy forces a substance to transition from a solid phase right into a liquid phase, and ultimately bursting into a gas phase. Now, what's really interesting about this slide is the story being told by those red arrows and the little vibration lines drawn around the particles. As we add heat energy, we are quite literally pumping kinetic energy right into the system. The particles in the solid start to vibrate more and more vigorously, until boom, they disrupt that rigid structure. They move faster, They spread apart, and they smoothly transition into a liquid, and eventually push apart into a gas. Let's look closely at the first major phase change on this journey, melting. Think of a solid block of wax being placed into a hot pan. As the heat transfers into that wax, those tightly packed particles gain a ton of kinetic energy. They vibrate so fiercely that they finally just overcome those strong forces holding them rigidly together. The whole structure collapses into a much looser arrangement, and the solid physically melts into a liquid. As we continue heating our liquid, it's going to turn into a gas. But hold on, there is a very common point of confusion right here that we really need to clarify. Both evaporation and boiling turn a liquid into a gas, but they actually operate quite differently. Evaporation happens only at the very surface of the liquid. It's a much slower, cooling process, and it actually occurs below the boiling point. Boiling, on the other hand, is a rapid, intense process that happens all throughout the entire liquid once it hits a specific high temperature limit.
That brings us to section 4, cooling down, removing energy. Let's totally reverse our engines for a second. Imagine we take those hyperactive, crazy gas particles and we just start stripping that thermal energy away. Notice the blue arrows pointing backwards here? When we remove heat energy, we are effectively stealing away the particle's kinetic energy. As a gas cools down, its fast-moving particles start to drastically slow their roll. They lose the energy they needed to stay spread apart, and so the natural attractive forces between them just start pulling them right back closer together. And that brings us perfectly to condensation. This is the exact process where a gas changes back into a liquid state upon cooling. To visualize this one, just think about what happens when warm, moist air meets a cold surface, like the lid of an ice-cold drink sitting outside on a hot day. The invisible water vapor gas in the air loses its energy to that cold surface, slows way down, and clumps together to form those visible liquid water droplets you see. Let's move to and see how this builds into the final cooling stage, shown right here. If we continue to remove heat from that liquid, say by sticking it into a freezer, the particles are forced to slow down even further. Eventually, they lose so much energy that they literally can no longer slide past one another. They get locked right back into a fixed, rigid, solid structure, and we of course call this freezing. And finally, section 5, phase changes in reality. Let's ground this in the real world. So we've spent a lot of time zoomed way in on abstract theory. Now let's zoom back out to your macroscopic daily life. So the crucial point is applying what we've learned. Melting, that's just the candle wax turning into a little pool of liquid when lit. Evaporation is that pesky puddle of water slowly disappearing from the pavement after a summer rainstorm. Condensation is the thick morning fog or the sweat forming on your cold soda can. And freezing is simply putting tap water into a tray and letting it turn into solid ice in your freezer. At the end of the day, it's all just particles gaining or losing kinetic energy. But before we wrap up, I want to leave you with one final, truly fascinating thought. We just mapped out the journey from solid to liquid to gas. But what if we don't stop there? What happens to the particles of a gas if you were to add an extreme, massive amount of heat? Well, have you ever heard of plasma? When gas gets so unbelievably hot that the particles actually start to break apart and become electrically charged, you get a fourth state of matter. It's the literal stuff that lightning and stars are made of. But hey, that is a mystery for our next lesson. Keep observing the amazing world around you, and I will see you in the next explainer.